Okay, so today I want to talk about, finish talking about Casanova-Mumford regularity and prove some of the theorems we stated last time. So there are going to be 3 parts of the talk. And the first, I want to prove this, use vanishing theorems to give the proof of this regularity theorem. So let me start by recalling what the statement was. So remember we had this notion of Casanova-Mumford regularity, which had to do with vanishing of twists of an ideal sheaf that measures the algebraic complexity of a subvariety. And so we had a smooth n-dimensional variety X in PR. And I'm always working over C, because I'm going to be using vanishing theorems. And E is the codimension. And we wanted to assume that we know that X was cut out as a scheme by hypersurfaces of degree D. So we want to assume that the ideal sheaf of X twisted by D is globally generated. So it's cut out scheme theoretically by hypersurface of degree D. And then the assertion, the theorem was that the regularity of X is at most what? The codimension times the degree minus 1 plus 1. And it doesn't exactly matter what this number is, but I remind you that this is the regularity of a complete intersection of hypersurfaces of degree D. So we're saying that anything like this that's cut out, any smooth subvariety of projective space that's cut out by hypersurface of degree D has regularity no worse than a complete intersection. And in fact, we'll see a little bit later that those are the only boundary cases. Okay, and so the idea is this is proven with vanishing theorems, and I'm going to explain it using multiplier ideals. But as I was preparing the talk yesterday, I kind of had this guilt attack, because, I mean, to prove this with vanishing theorems is really fast, and the proof with multiplier ideals is really the same thing, but it makes it sound more complicated. So I feel a little bit guilty about making it sound more complicated than it is. So let me quickly tell you what the idea is. And then you can write down the proof in 5 minutes, and then you'll have some time left over while I talk about multiplier ideals. So the idea is this sort of classical thing. We're just going to consider the blowing up of projective space along X. So we'll consider U, I'll call it P prime. So this is the blowing up along X of PR. So this maps down to PR. And I'll always use H for a hyperplane line bundle. So H will be, I'm going to mix up divisor and line bundle notation. So H will be the pullback of O of 1. Except I apologize in advance. Sometimes when I'm working on PR, I'll call H the hyperplane divisor here. But I hope it doesn't cause any confusion. And then E will be the exceptional divisor. Okay, and now what does this hypothesis mean? So, and the point is, since X is smooth, P is the smooth variety. That's what's important. We know that P is a nice variety. And then the hypothesis to say that it's cut out by equations of degree D, so when I blow up, then the ideal sheaf turns into the exceptional divisor, so to speak, and so that this divisor, this linear series on the blow up is globally generated. So this is, in particular, it's Neff. And so now you just apply vanishing. So that's somehow going to be apply vanishing theorems on P prime. So that's really what the idea is. And if you're just willing, I mean, it takes 5 minutes. In 5 minutes, I could give the complete proof like this. But I'm going to sort of, just because I think it's fun, and we can use the same method to not prove a more general statement, later on, I want to explain the same argument with multiplier ideals. So again, this isn't really necessary, but maybe it's a little bit more geometric. Okay. It's I'm sorry. It's globally generated, is what I wanted to say. Sorry, that's a typo. Hence Neff. Well, on P prime. So this is the pullback of. So what's happening is you have this so you have this X here, and you have this hypersurface of degree D cutting out X. So when you pull back to the blow up, the proper transforms of these hypersurfaces are in this linear series. And then to say that the ideal sheaf is globally generated means that this linear series is globally generated on. So this is, I mean, this is a linear series of divisors. This is some So you've just, it's the usual thing. You've turned an ideal into a line bundle. Okay, so let's spend a few minutes talking about multiplier ideals. Okay, so we'll leave this aside and we'll come back to a few minutes. So let's start with P as some smooth complex variety. And for the moment, this is a local discussion, so it doesn't need to be projective. And we start with a Q divisor on P, so something like AI di, a Q divisor. So it's a, let me make it an effective Q divisor. So it's a rational, a non-negative rational linear combination of divisors. And then you can associate to the pair x comma d a multiplier ideal. So that's an ideal sheaf that somehow measures the singularities of this divisor d. So we can associate to this Q divisor on this smooth variety a multiplier ideal sheaf so let me call it J of D or sometimes J of PD. So this is going to be an ideal sheaf, a sheaf of ideals on our smooth variety. And you should think of this as somehow in some interesting way it measures the singularities of D somehow. And the way it's going to measure the singularities of D is the worse or the more interesting are the singularities, the farther is this ideal from being trivial. So somehow the deeper this ideal lies inside O of P. And there are various equivalent constructions. So let me mention two. So the first construction is a more analytic construction. So D is a linear combination of these components. So let's say the GI is a local equation for the ith component, for DI. Okay. So then locally, this is kind of a more analytic, so then we can define J of D is locally. So we can think of it locally as the set of all holomorphic or polynomial functions H. So let me write it down and then I'll comment on it. So they're going to be defined by some integrability condition. And the condition is that the modulus squared of H divided by the product of the GI to the two AI. So this function should be locally integrable. Okay, so let's think for a minute what this means. Let's try to parse this for a second. So supposing you're at a point away from the support of this divisor. So supposing you're at a point where none of these GIs vanish. Well, then just the function 1 over the modulus of this GI, that's a perfectly nice function. So it's certainly going to be locally integrable without any H. So if you're away from the zeros of any of the GIs, then you can take H to be 1 here, and you get an uninteresting, I mean, what you get is a trivial ideal. On the other hand, supposing you're at a point where one of the GIs vanish. Well, then the denominator here is becoming 0. And it may be that this is that even if you have a 1 here, it may be that the reciprocal is still integrable. But on the other hand, it may be that it's not. And if it's not, you might have to multiply by something on the numerator to make it make the top vanish along with the bottom so that it's integrable. So in this sense, it measures the singularities. The worse, the more interesting are the vanishing of the G's, the more conditions those are imposing on H in order that this be integrable. So that somehow.
How about the denominator is also 2 times AI?
Yeah, I mean, yeah.
Special reason why you have 2 and both?
Well, I mean, it's an L2 thing. So, I mean, I'm having a 2.
Why not just take normal H divided by
yeah, I mean, it's just, I guess I could. No, because this is, I mean, you can have, one, I mean, that's a different integrability condition. It's a, I mean, if you want to do that, then I could make it locally L2, but it's a somewhat different condition, yeah. Okay, so that's the sort of construction 2, which is kind of closer to algebraic geometry, is we take a log resolution of these data. So you take mu from p prime to p, a log resolution of the pair PD. So that means you take a resolution of singularities of D, so that when you pull everything back, that the pullback of D plus the relative canonical bundle, everything should be in normal crossing singularity, in normal crossing form. And then let me just write down what this is. So what this is we're going to take the push forward of O of P prime. So I'm going to look at the push forward of some divisor. And what I'm going to do is I'm going to take the relative canonical bundle, K of P prime over P. And then what I'm going to do is, while I just pull back D. And so this is some Q divisor upstairs. And then I take its integral part. And I subtract it. So it's not the most intuitive definition, but we'll do some examples in a second, and you'll see kind of how it works. And this is actually indeed an ideal sheaf. So this is living inside O of P, because when you push forward the relative, P and P prime are smooth. The ambient spaces are smooth. So when you push forward the relative canonical bundle, you just get O of P. So this is, you're putting more conditions on that. So it's all, functions downstairs that have some funny vanishing with respect to the divisors appearing in the resolution. Okay, so let's see if I remember how this process works. So let's see some. Yeah, I'll do it in a sec. So if the DIs are already normal crossing, yeah, okay. If D is already normal crossing, then this is independent of the resolution. So then I can take P prime equals P, and then I'm just rounding. I'm just taking the integer part of the D. So it's O of minus the integer part of D. Yeah, so I'll do some some examples in a sec. So the thing about this erasing method is it can come in a good moment or a bad moment. It could come in a moment when everything's clear and one observes it, or it can come in a moment when it's, okay, so let's see. This really is much quicker to go horizontally, isn't it? Okay. Okay. Okay, so let's see some examples here, some remarks, some examples. So what does it mean for this ideal to be trivial? So that means that when you take mu upper star D, it doesn't impose any conditions on the relative canonical bundle. So in algebraic geometry, that's just says, so to say that this ideal is trivial means more or less by definition that the pair P comma D is what's called column-a log terminal. So this is one of the classes of singularities that comes up in the minimal model program. So, I mean, I'm not, either this is, depending on your point of view, one side is helpful for the other or neither. But in any event, the point of these multipliers, I'm sorry, this is trivial. So to say that you get a trivial ideal means that it's column monolog terminal. So exactly in the column monolog terminal case, these multiply ideals are trivial. So somehow it's in the non-log terminal case that they get interesting. Okay, so let me do one slightly non-trivial example here. So let me take P to be affine space of dimension E, and then let me take a E plus 1, so I'll take the case 2. Let me take E plus 1 general hyperplanes through the origin. So let me take A1 through AE plus 1 general hyperplanes through the origin. And it doesn't exactly matter that they're hyperplanes, but I want them to be smooth and kind of a nice picture like that. Okay, so I want to look at the Q divisor, so I want to, let's set D to be, how do I want to do this? I want D to be E over E plus 1 times A1 plus A E plus 1. So for example, here, my D would be 2/3 the sum of these divisors. So that's a perfectly good Q divisor. And notice that we've rigged things so that the multiplicity at 0 of D, which means the obvious thing, is exactly E. So we've rigged it. We've got a divisor that has multiplicity E at the origin, but the multiplicity away from the origin is strictly less than 1. So that's what you can do by working with Q divisors. OK, and now what I want to claim is that then, if we take the multiplier ideal of this D, what we get is just the maximal ideal of the functions vanishing at the origin. So maximal ideal of the origin. So that you don't get any condition on these away from the origin, but at the origin, this condition here, the integrability condition, is that the function should vanish. OK, so let's see how this is. And this is basically the model, and going to be the model of what comes up in the proof of this regularity theorem. OK, so let's do the computation. So the point is, if you have general hyperplanes through the origin, you can assume that you resolve that, you get a log resolution by just blowing up the origin. It's the simplest thing you could get. So we can assume that mu from the p prime, the blow up of the origin in C to the E to P, that this is a log resolution. There's a resolution. Right, because let me draw the picture when E equals 2. So we start with something here, and then we blow up the origin, and then we're going to get the picture is just going to look like that. And if you're worried about why you can assume this, the way to think about these things is I might as well just start upstairs and take my, start with the A prime up, these divisors upstairs, and then get the A's by pushing them down. So we'll write, so here's a AI, and here's its proper transform, AI prime. So what this means is the mu upper star of AI will be the exceptional divisor with multiplicity 1 plus its proper transform. And to say that this is a log resolution means that the sum of the AI primes, these guys, is a simple normal crossing divisor. OK. OK, now let's see what happens when we go to this funny definition of the multiplier ideal. Let's see, should I, well, I'm asking myself, should I keep the definition up? Nah, it's too complicated. So, OK, so let us compute the multiplier ideal then. So, OK, so what happens when we have to remember that the multiplier ideal, remember the multiplier ideal is mu lower star of OP prime, KP prime over P minus the integer part mu upper star D. So that's the multiplier ideal. OK, so what happens with this mu upper star D? So we just, mu upper star D is defined by linearity. So mu upper star D is just E over E plus 1 times the sum of the AI primes. But then I also have plus, I've rigged things so that the total multiplicity is E. So plus E times the exceptional divisor. right? Because mu upper star of each AI is E plus AI prime. So altogether, I've got E times E, and okay. And then the relative canonical bundle is minus, E minus 1 times the exceptional divisor. Okay, but now here's the interesting thing. So what happens when I round? So the fun thing is what happens when I round mu upper star d, so when I take the integer part. So the point is when I take the integer part, these coefficients are less than 1, so this term completely disappears. Once I take integer part, the component, the AI primes disappear. So all that's left is E times E. So the whole point about rounding is that I've kind of concentrated all the interesting stuff at the origin. And so now when I take, K P prime over P minus mu upper star E is just, minus mu upper, round of mu upper star D is just minus E. And when I push down minus E, what I'm looking at is functions that vanish at the origin. So this is kind of how this works. The whole point is this sort of funny rounding. So that's the interesting thing that happens. Okay, so these are quite interesting ideals. There's a lot to say, but this is so the construction of these things is local. But what gives them their punch is that they satisfy vanishing theorem. So again, if you know the Kawamata-Vivek vanishing theorem, you can kind of believe that this is kind of it's built into this. It's a way of packaging this. So here's the Kawamata-Vivek Nadal vanishing theorem. And again, it's kind of built into this story here somehow. So here is in the global setting. So we assume that we're working in a smooth projective variety. So P is projective. Okay, and so this is a global theorem. And let's let L be a line bundle on P. And we'll let D be, again, an effective Q divisor on P. And we want some positivity condition on L minus D. And so the positivity condition is we assume also that L minus D, so this is a Q divisor. So this thing should be big and nef, or nef and big. So is nef and big. So for example, it should be ample. So this is essentially a Q divisor, so it makes sense to talk about amplitude for Q divisor. So this is a well-defined thing. So this is, okay. And then the assertion is that we get a Kodaira type vanishing for L, but corrected by the multiplier ideal of D. So then the assertion, the vanishing theorem is that HI on P of O, P of KP plus L times the multiplier ideal of D, that these cohomology groups vanish for positive I. So this is the basic vanishing theorem for multiplier ideals. So let's look at some special cases. So supposing that L is already ample. Okay, well then we might as well take D, for example, 0, and then this is just the multiplier ideal of the 0 divisor is just O. So this is Kodaira vanishing. On the other hand, maybe L isn't ample, but you can find some kind of Q divisor. L is of the form some interesting Q divisor plus something ample. So then you get a vanishing theorem for K plus L, but you need to correct by this Q divisor, something having to do with the singularities of the Q divisor associated to the non-amplitude of L. So on the one hand, this gives you a vanishing theorem involving non-ample L's, where somehow this divisor D corrects for the failure of amplitude. Another way to think about this theorem, which is how we're going to be interested in using it, is that you might have an interesting line. L might be ample, but you might want to prove a vanishing theorem not just for line bundles, but for ideal sheaves. So in our situation, L will be ample, but you'll still find some interesting Q divisor that has an interesting multiplier ideal. And so then you get a vanishing theorem for k plus L times an ideal sheaf. And so that's how it's going to be important for us. For the vanishing theorem, for the regularity theorem, one doesn't actually need Q divisors is the point. But in any event, let me show you a nice application of this. And then we'll go, as I say, this is not the quickest way to prove the regularity theorem, but it's fun to see multiple ideals. Okay. Yeah.
If D was already a Z divisor,
Yeah.
is the multiplier ideal somehow better?
No, because, well, it depends. I mean, see, the point is, no, I mean, that's what we're going to use, because the point is you need to take a log resolution of D. So it has to do with, even for Z, we'll see in a minute, even for Z divisors, you get interesting stuff. I mean, like the thing, you get interesting stuff when you kind of pass to resolution. Well, yeah, let me be careful, I'm sorry. I'm saying something wrong. The multiplier ideal of a Z divisor is just that divisor itself. That's, as it turns out, that's uninteresting, yeah. You can, well, yeah, sorry, yeah, so that, but the typical thing is you have something, you know, well, let me just show, let's just, yeah. There are also multiplier ideals for ideal sheaves, and then you get something interesting. Oops, no, that's definitely not what we want to do. Okay. Yeah, so let me show you a multiplier ideal proof of a classical theorem of Zariski. So this is kind of, so you know, how do you prove these vanishing theorems? How do you know, where does the Kawamata-Vivek vanishing theorem come from? Well, that's typically proven with, you know, you have a Q divisor, you take cyclic coverings and so on, and then you apply vanishing on a cyclic covering. And I think the first vanishing theorem was, the first vanishing theorem of Q divisors was somehow proven by Zariski, who took cyclic coverings of curves, cuspidal curves in the plane, and then studied the irregularity. These things. So let me tell you what Zariski's theorem says. So I remind you that there's a classical theorem that if you take an irreducible plane curve of degree d, a curve in P2 of degree d that has nodes, then the nodes impose independent conditions on curves of degree d minus 3 or d minus 2. So Zariski wanted to prove a similar statement for curves with cusps. So his statement is this. So let's let C in P2 be a reduced plane curve with a certain number of simple cusps. So reduced plane curve of degree d with some simple cusps, at some certain number of points, at some set S. So S will be, so let's say, x1 through x tau. So we get a finite set of cusps. So the curve looks kind of like this. It might have some other singularities as well, but it has some cusps, and we don't care. It's supposed to be a cusp. We don't really care. And by a simple cusp, I mean locally z squared minus w cubed equals 0. So it's just simple cusp like that. Okay, so it has a certain number of simple cusps and maybe some other singularities. Don't really care. Okay, and then the claim is that then, so we've got some finite set of points where we have cusps. And then the claim is that then the points of S impose independent conditions on curves of degree, some funny numbers, degrees k bigger than 5, 6, d minus 3. So in other words, if k satisfies this inequality, the H1 of the ideal sheaf on the twist of the ideal sheaf of these cusps, twisted by k, equals 0, if this condition holds. Okay, and hence, just since we're talking about regularity, just say, and so hence, this finite set is k plus 1 regular. For a finite set of points, regularity is just governed by the H1, because the higher cohomologies of the ideal vanish automatically. Okay. So, okay, let's prove this. So again, so this is the kind of a good example of how you use vanishing for multiplier ideals. So there's first of all a local calculation. So if you have a cusp like this, a curve like this, what coefficient do you have to put in front of this thing so that you just first see the multiplier ideal? And that's a famous computation that I'm not going to do, but I'm sure everybody. So if you take a cuspidal curve, what multiple of it is just fails to be log terminal, and that's called log canonical threshold. So a famous calculation says that what's called the log canonical threshold, log canonical threshold of a simple cusp is 5, 6. So in other words, if you take this cusp and you multiply by 5, 6, what you get is you get a non-trivial multiplier ideal. And if you multiply by anything less, you get a trivial multiplier ideal. And you just have to do the famous log resolution of a cusp, and you just have to compute. Okay, so what that means is if we take this curve, so here's our curve C, and we scale it by 5/6, we're going to pick up the ideal. We're going to pick up the maximal ideal of each of these points in the multiplier ideal. So what that means is that if we take the multiplier ideal, well, so we'll take a 5/6 times C, so that's our Q divisor, that this multiplier ideal vanishes at each of the cusps. It just vanishes at each of the cusps. Now, there may be other singularities, and it may also vanish at other points, but in any event, this ideal is contained in the ideal of the cusps. And since everything is reduced, also, the ideal of the cusps modulo this ideal is supported on a finite set. So this may have other zeros besides the points, beside the cusps, but in any event, the quotient is zero-dimensional. So if we get a vanishing for H1 of this, that implies a vanishing for H1 of that. So we don't care about the difference somehow. Okay, now we need to what is the degree of this curve? Well, this thing here, C has degree D, so this thing has degree 5/6 D. So, and then what this condition means, see that of course is where the 5/6 comes in. What this condition means means that if I take K times the H, so now H is just a line in P2, so I hope that's clear. I take K times H minus 5/6 C. So K times H minus 5/6 C, this is, let's see, now I'm suddenly worried about my numbers. So this is of the form, let's see, do I want to, no, I think I'm okay here. So this is of the form KP2 plus ample, right? Let me see. Let's see. Yeah, so I want to say that K, this is all very confusing. If K is bigger than 5/6, yeah, K minus 5/6 D, so this has degree K minus 5/6 D. So K minus 5/6 D is minus 3, so that's the canonical bundle of P2. And then because I have a strict inequality here, I get something ample. Okay, so vanishing applies. So I get the H1 of the ideal sheaf of the multiplier ideal, O of K times the multiplier ideal. And then that implies that the H1. Okay, so this is kind of how it works. So what we've done here is all the line bundles in sight are positive, but we've found an interesting divisor in a linear series, and then that gives us an interesting multiplier ideal, and so then we get an interesting vanishing. Okay, so good. Okay, so now let's prove this regularity theorem. So as I say, we could have proven the regularity theorem 20 minutes ago and been done with it, but in any event, oh, this was a mistake, sorry. My apologies. We could have done the regularity theorem 20 minutes ago and been done with it, but I think it's fun to see multiplier ideals. So let's see this. maybe isn't wet enough. Okay. Okay, so let's now see the proof of the regularity theorem. Okay, so we have, so what was the setup? So we have a smooth, we have a non-singular smooth n-dimensional subvariety in PR, and Ix of D is globally generated. And we wanted to show that it has at least, at worst, complete intersection regularity. Now, so of course, when you do these regularity things, there's always a certain amount of numerology to do, and it's not a spectator sport to do the numerology. But if you go back and check the numbers, you'll see that it's enough to prove the following. So to prove the regularity theorem, it's enough to prove the vanishing HI of PR of Ix twisted by K equals 0 for I positive, and it turns out that this is what you want to do, E times D minus R. So remember, E is the codimension. So this turns out to be enough vanishing to give you the regularity that I stated before. Now, if you actually go and do this for yourself, there's one remark to be made. So note that when you want to prove the regular, I mean, we want to prove a theorem about the vanishing of an ideal sheaf of some subvariety. So as a general principle, the cohomology of ideal sheaves, there's sort of 2 or 3 different things that can happen. The H1 of an ideal sheaf has to do with the embedding. That measures whether or not hypersurfaces of a given degree trace out a complete linear series. The H2 of an ideal sheaf is the H1 of the structure sheaf of X. The H3 of the ideal sheaf is the H2 of the structure sheaf of F, if you just run the exact sequence. So the cohomology from H2 all the way up to Hn plus 1 has to do with cohomology of the structure, intrinsic stuff, the structure sheaf itself, of X itself. And once you get to if you have an n-dimensional variety, once you get to Hn plus 2 of the ideal sheaf, that would be Hn plus 1 of the structure sheaf on X, which is 0. So the remark is you should always note that the vanishing for I strictly bigger than n plus 1 is free. So there's nothing, you don't really need to prove anything. So then if you work out the numbers, you'll see that this is what you need to worry about. Okay. So now we're actually going to just do the same thing that we did in our example before, where we had hyperplanes through the origin. So let's choose general hypersurfaces. A1 through AE plus 1, so E is the codimension. So these will be hypersurfaces of degree D passing through X. So I have some globally generated ideal sheaf. I just take general hypersurfaces. So again, the transverse picture is where if this is X here, the transverse picture is just what we had before somehow. And then I'll set D to be the same thing as before. I'll set D to be E over E plus 1 times the sum of the AIs. So, locally in the transverse direction, this looks more or less like what we had before. Okay. Now, what's the key claim? So the key claim is that the multiplier ideal of this D on projective space is just the ideal sheaf of X. So I've realized the ideal sheaf of X as a multiplier ideal. Okay, well, what's the reason for this? So morally, the reason is just what we said before. I mean, morally, and any point of x that looks locally in the transverse directions to x, it looks locally like the same picture as before. You have to be a little bit careful about that because you can't simultaneously do that at all points of x. So you need to argue a little bit, but it's the same argument as before. So the reason is that since x is smooth and Ix is twisted by d is globally generated, then we can assume that just the blow-up of x is a log resolution of this divisor. So we can assume by taking these divisors generally, we can assume that the blow-up along x of PR is a log resolution of the pair of PR comma D. So again, it's just as the argument before. We can assume that we get a log resolution just by blowing up x. And again, the quickest way to convince yourself of this is you first of all blow up x and you get a smooth variety. And then just as we said before, this d times the hyperplane section minus e is globally generated. So you take you just take the proper you take ai prime. So this is a globally generated linear series. And so if I take general elements here, their sum will be a normal crossing divisor. And I just take ai to be the image of this thing here. So the quickest way of doing it is to just work upstairs first and then. OK, but anyway, and now we're done. Because, OK, and so once you know that this is true, then it's exactly the same computation as before, says that this is true. So now compute as before, as in earlier example. OK, and now we're done, because we've realized we're interested in the vanishing theorem of the ideal sheaf of x. But we've realized the ideal sheaf of x as a multiplier ideal, and so now we just see what vanishing says. OK, so let me. Whoops, yipes. I've detached it somehow. Oh, well. Let's see. Well, we'll worry about this at the break, I guess. OK, and so now we're. Whoops. Okay. So now we're done, right? So now we just apply vanishing. So we apply vanishing. So we take. So what is the degree of? So this Q divisor D, is linear equivalent to what is the degree of this D? So each of the AIs has degree D. So the sum of the AIs has degree D times E plus 1. You divide by E plus 1 multiplied by E, you get DE. So the total degree is of this divisor D is DE. Okay, and if M, so now let's suppose that M, is bigger than or equal to what? DE plus 1. So then of course, and let's take L to be O of M, OPR of M. So then, so L minus D is actually ample, because I've thrown in one extra copy of O of 1. And so I get the vanishing, and so we get the vanishing by the vanishing theorem of H1, well, HI, on projective space of what? Of OP. Now I have this M, but then I have minus R minus 1, because that's the canonical bundle of projective space, times the multiplier ideal of D, which is just the ideal of X. And this is 0 for I positive. And so I get DE minus R. So that's what I get. Okay. Let's see, let me go a couple more minutes and then we'll take the break a little bit late because I want to finish this here. So, okay, so you see the point about these multiplier ideals is that they have vanishing theorems built into them. And as I say, we could, to prove this particular theorem, you could certainly avoid multiplier ideals because we're not really using Q divisors in any essential way. But anyway, it's kind of, I think it's fun to see how multiplier ideals work. The other thing you might ask is, I mean, what happens if you do the same thing when x is, let's say, reduced and irreducible, but maybe singular? Well, you can, so take a possibly singular x where the ideal sheaf twisted by d is globally generated, and you can make exactly the same construction, and then if you form the multiplier ideal, exactly the same vanishing hold. So the point is that multiplier ideals always come with vanishing. But the place that it's essential to use the singularity, the smoothness of x, is that in the general case, you get a vanishing for a multiplier ideal, but that's not quite the ideal sheaf of x. It differs from the ideal sheaf of x along the singularities. So you get a good vanishing theorem, but you don't quite know how to relate the thing that vanishes to the cohomology of the ideal sheaf. So that's the kind of missing point. But is what? Something is known, but I don't think this theorem is actually known in positive characteristic. I think, I'm not, people have looked at that, but I don't think it's really known, right? So I don't think so. I mean, because even the sort of more naive proofs use vanishing. Yeah, you blow up and apply vanishing on them. So. Oh, yeah, it's unclear, right? But let me just end with one, again, this isn't necessarily terribly of any great importance, but it's kind of fun. So what I wanted to see some more geometry in the algebra. So I want to end up before the break with I had said before, so we have a certain regularity theorem for subvaries, and I said before that the worst possible cases are when you have complete intersections. So let's see how we prove that. So let's consider, xn and PR is above. So Ix twisted by d is globally generated, x smooth. And let's suppose that then what I want to say is that then the regularity of x is equal to this bound we have. So reg x is equal to whatever we had, e times d minus 1 plus 1. So we saw that this is the regularity of a complete intersection. What I want to claim is that that's the only case. So if and only if x is a complete intersection of hypersurfaces of degree d. Okay, so that we get exactly the only possible border cases for these complete intersections. So we get kind of a complete picture. Okay, so let's quickly, I'm going to assume that x is at least a curve. Okay, so here's the funny thing that happens. So of course we know one direction. So let's assume that assume that we can't do any better than this. So assume that x is not whatever it is, e times d minus 1 regular. And then we need to show that it's a complete intersection. Okay, now the point is that you see the way these vanishing theorems work. So the definition of regularity is it's a vanishing for twists of the ideal, but it's a sliding vanishing. As you take higher cohomologies, you want smaller and more negative twists. Whereas the vanishing theorem is a uniform statement. You get a vanishing for a given twist for all the higher cohomology groups. So if you're on the boundary, if you think about it for a minute, there's going to be only one cohomology group that obstructs the vanishing of this. In other words, we have all the vanishings needed to apply this, all the vanishings needed to get this regularity except for one. And the one, it turns out to be, so then by the proof is an HN on X of the regularity theorem. There's one particular group that has to be non-vanishing, and it's this. If you write it, if you change it from a vanishing on the ideal sheaf to vanishing on X, you get DE minus R minus 1 is non-zero. So that's the only cohomology group that keeps you from getting a better regularity statement. And then what's Serre-Dual to this, so in other words, if we take the canonical bundle, and again I'm going to use H for the hyperplane line bundle, minus DE minus R minus 1H, that this line bundle should have a section. So this divisor should be effective. Okay, so what I'm saying, the only way this can happen is that the canonical bundle of X has to be really very, very positive, is what that's saying. And so now, given that X is cut out by equations of degree D, we need to say that that condition forces X to be a complete intersection. Let's see, I'm making a mess of this. Okay, so let's see how this goes, and then we'll take a break. Okay, so now we need to say that that condition forces X to be a complete intersection. Now, if it's going to be a complete intersection, it's kind of clear what it has to be a complete intersection of. What we have to do is take E, that's the codimension, hypersurfaces of degree D vanishing on X, and those have to cut out X. If this is going to be true, that's what has to happen. So let's choose general hypersurfaces. A1 through AE, these will be hypersurfaces of degree D vanishing on X. Okay. And so really, what has to happen now is that X, if it's going to be true that X is a complete intersection, it has to be the complete intersection of these. So let's look at the intersection of these. So let's let Y be A1 through AE, the intersection of A1 through AE. So then what does Y look like? Well, Y contains X as an irreducible component, but it may have some other stuff too. So it looks like X union X prime. So here's the picture. We have this X here, and we take E, that's the codimension, general hypersurface of degree D vanishing on X, and since this is globally generated, X will be a component of this, but there may be some other stuff coming in as well. So we might get some X prime. And what we need to show essentially is that X prime is 0. And in fact, it's enough to show, the trick is going to be to look at X intersect X prime. So it's enough to show that X intersect X prime is empty because in any event, Y is connected. Complete intersections are connected. So we need to say that this other stuff, this kind of parasitical component coming in doesn't meet X, and then we're done. Okay. Okay. Now, let's ask ourselves, let's again compute the canonical bundle of X a different way. So supposing Y were equal to X union something that didn't meet X, what would it look like? Well, you see, the point is that then you can convince yourself that the canonical bundle of X looks like what? Well, the canonical bundle of Y is exactly, well, let me see, DE minus R minus 1 H restricted to X. So this is the term coming from, this is the canonical bundle of Y. So if X were a connected component of the canonical bundle of Y, this would be its canonical bundle. But we lose a little bit the intersection of X prime intersect X. That's a divisor on X that contributes negatively to the canonical bundle. So this is minus, if you think about it a little bit, restricted to X. So this is what the canonical bundle of X looks like. So the more this other component comes in and hits X, the more negative is the canonical bundle of X. But now, you see, this is saying that the canonical bundle of X, this is saying that this thing minus the canonical bundle of X is effective. That's the reverse inequality. So, so if we combine it with star, this is star. So then star implies that X prime restricted to X is 0, so we're done.
So what do you mean by minus X prime?
No, it is. They intersect in a divisor. So if I have a complete intersection, it's connected in codimension 1. Yeah. So x prime, it comes in and meets and divides it. Okay, so that's it. So why don't we take a break there? I'm sorry I'm a couple minutes late, and then we'll finish up after the break. Okay, so the next thing I want to talk about is the construction of ideas, so geometric construction of ideals with large regularity. And then I'll end with a quick couple of remarks about Casanova type regularity bounds. So ideals with large regularity. So remember, as I mentioned last time, there's this kind of poorly, sort of mysterious but fascinating dichotomy between what, if you talk about regularity, between what happens for the ideal of smooth varieties, which we've just seen are kind of behave very well, and the arbitrary ideal sheaves. So the regularity of arbitrary ideal sheaves can be really terrible. But the interesting thing there is to construct examples. So the sort of examples that the algebraics construct are entirely combinatorial in nature. So I've always felt that it's kind of an interesting problem to construct geometrically some ideals of where the regularity is worse than complete intersection. So construct geometrically some ideal sheaves, ideals J, let me call them I, a little bit later I'll call them J maybe, but anyway, in OPR. So again, let's sort of focus on ideals that are generated in a certain degree. So with the ideal sheaf twisted by D globally generated, but so that the regularity is much worse than complete intersection regularity. So let's just say, such that the regularity of I is much bigger than R times D, for example. So remember then it's known that there are examples where it's a polynomial in D with coefficient, something like 2 to the R, something like that. But in any event, let's be more modest and just find examples. It's not so easy to construct examples where the regularity is worse than smooth complete intersections. And recently there's been some progress that I'll mention by Brooke Ulrich. So, but the important thing is not that like people didn't know that ideals like this existed, but to kind of construct them geometrically. Of course, the algebraists who are mainly interested in this problem don't care about geometric constructions. But anyway, I do. I'm maybe the one person that does. So, okay. So what would be the idea for how to do this? So, well, for example, e.g., you could look for an ideal, for ideals I, with a presentation, so with a minimal presentation. I'm not going to say exactly what that means. Minimal presentation of the following form. So, okay, so we have this ideal here. And we want to say that it's generated in degrees, that it's cut out by hyperserved degree d. So that means it should be generated by a bunch of O minus d's. So we should get a bunch of O minus d's mapping onto that. Now, remember, if the regularity is measured by how many, how big the jumps are when you go up through a resolution. So one thing that would make it very irregular would be to have the next step to have the syzygies among these hyperserved degree d be very large. So n much bigger than r times d. So if you can find an example like this, and when I mean minimal is that you can't find an example with, in this example, you can't find smaller n's that work. So if you can find an example like this, then this will obstruct this will force the regularity to be big. And okay, so now what is it that makes an ideal an ideal? Well, to be an ideal sheaf means you're in a coherent subsheaf of O. So really, you need to kind of find a complex from O, direct sum of O minus d's to O, and then the kernel of that map should have the sort of syzygies among these degree d hypersurfaces should have very large degree. And it's not so obvious how to do that. But what the idea is this. If you don't look for ideal sheaves here, but you look, for example, for vector bundles, it's really easy to find vector bundles with a resolution of this shape. So it's easy to find, let's say, vector bundles on projective space, let's say even on P2. That's the smallest place you could look. Bundles on P2 with a resolution of this shape, of this sort. And then Ulrich's idea is you try to use these, so use these to build interesting, in some bigger projective space, ideals on PR. So in other words, the idea is to pass from vector bundles on a small projective space to ideals on a big projective space. And somehow so let's see how that goes. Okay, so this is, as I say, it's a construction of Bruch-Ulrich. So here's her construction. There are various parameters in the construction. I've chosen the numbers kind of in the first simplest way I could to do the computations. I mean, you can vary the numbers a bit, but anyway. Okay, so I want to start with the vector bundle on P2. So step one is it's elementary. So this is elementary. I'll say in a minute where they come from. But for every k bigger than 1, there exists on P2, I'm going to go, there's going to be a long picture here, can't help it. So exists on P2 an exact complex of vector bundles, complex defining a vector bundle which I'll call E sub k. So let's see how this goes. So I need some room here, so I apologize for. Okay, so over here, maybe I need to go a little bit farther. Let me go farther over it. Better to be too far than not far enough. Okay, so I'm going to write down, so on the right, I have on P2 O of 1, I'm going to have k choose 2 copies of this. Okay? And coming into this, I'm going to have a direct sum of O's. And I'm having how many copies? K squared minus 1 copies. And coming into this, I'm going to have some O minus 1s. And how many do I have? I have k plus 1 choose 2 copies of O minus 1. K, it doesn't matter what the numbers are. But anyway, like this. And then this is the interesting thing. The kernel of this map is one line bundle of very negative degree. So I have OP2 minus K minus 1. So I claim it's quite easy to construct examples like this. Yeah, exactly. So what you do is you, this is what's one of these things called an Egan-Northcott complex. So you take a matrix, I forget what the size is, K by something or other, K by K plus 1 matrix. What? Well, no, you start, it doesn't have to be symmetric. You take a matrix of linear forms, there are various complexes you can write down. And this isn't the resolution idea, there are a whole sequence of complexes, but this is one of them. So there are a whole bunch of complexes. They actually come from Cazaux complex, but these are the next most elementary complexes after Cazaux complexes, and they're called, so you can write this thing down. Okay, and now our bundle is going to be this middle term here. So we're going to take EK to be the kernel. So this is exact. The complex is exact, and our bundle EK is going to be the kernel of this map, which is a co-kernel of that map. So you see what's happening here is that EK is if I twist it by 1, it's globally generated. And it's got, so in this picture, I mean, the example is going to involve a higher twist. But see, I have, and EK itself is a subbundle. Now, if this were just a copy of O, then it would be an ideal sheaf. But of course, if you have an ideal sheaf, when you twist it by 1 that's globally generated, then it's an ideal of a linear space. So you don't get a resolution like that. So here we have something twisted by 1 is globally generated. It lives inside some O's, but not just one copy. And there's this one very large degree relation among these linear things mapping onto E. So you can do this. So this is, I say, it's coming from an Egan-Northcott complex. So this is one of these Egan-Northcott complexes. Okay, and so what are the invariants of E? So, well, what's its rank? So the rank of EK is approximately, well, this is K squared, that's K squared over 2, so it's approximately K squared over 2. And EK twisted by 1 is globally generated. And what's the regularity of EK? Well, we can exactly read off the regularity, because this is, see, EK is sitting at the tail end of a little exact sequence like this. So the regularity of EK is exactly K. So if EK were an ideal sheaf, this is the kind of thing we're looking for, but it's not. But it's a higher rank vector bundle. Okay. Now, but now the idea is we'll use this EK to build an ideal sheaf. We're going to actually take, I think my numbers are in P6, but it doesn't, there are a lot of, as I say, there's a lot of degrees of freedom in this parameter. But what we'll do is we'll put the P2 in E6, and we'll use EK to build a really funny multiple structure on this P2. So, okay, so let's see. Okay. Okay. So now we're going to put this P2 in a bigger projective space. So I think I'm going to now consider P2. So we'll think of it as a linear space embedded linearly in some bigger projective space, and I'll choose P6. But there's a lot of degrees of freedom. There's nothing really special about P6. It's just the numbers worked out. Okay, so we're going to, here's my P2 and P6. And now what's the conormal bundle of P2 and P6? So the conormal bundle, P2 and P6, is of course just 4 copies of OP2. I'm sorry, let me do it like this. It's just 4 copies of OP2 minus 1. Okay. Now, what I'm going to do is, so now let me choose some number L. let me choose L so that the rank, well, let me do it down here. Let me choose L such that the rank of sim L of this conormal bundle, which is what? Which is L plus 3 choose 3. I want this rank to be bigger than or equal to the rank of E sub k. And let me just add 2. So, okay, so I want to just choose L like this. So let's see, what does this L have to be? So this is like L cubed over 6. This is like k squared over 2. So essentially I need L to be approximately, I want to do it fairly efficiently. So constant times k to the 2/3. Or what's equivalent, k is approximately, what, L to the 3/2. Okay, so I do that. Okay. And now, so what this means is, so the sim L of this thing is a direct sum of O minus L's, and it's this many of them. And now I'm going to take a twist of E, and I'm going to put it in a direct sum of O minus L's. See, so then there exists an embedding. See, E sub k lives in the direct sum of O. So one way to say it is that EK dual is globally generated. And so I can, EK dual with a suitable twist will be a quotient of the dual of that. So then, well, let me do it like this. So then there exists an embedding. And this is kind of very rough. We're just going to choose something kind of completely at random. There exists an embedding, a vector bundle embedding of EK minus L inside this sim L of the normal bundle of lambda in P6. And I'm saying something almost trivial. I'm saying the EK dual is generated by its global sections. So this thing dual is a quotient of a direct sum of OLs, and so I can just write it as a quotient of that thing. So there's almost nothing happening here. And I'm choosing this in a completely random way, which is the weak link of the construction so far. So I just choose some randomly like this. And I can do it because just I know. Okay, and now I'm done. So now we can, so this is now, so let's look at this. Let's see, I hope this is going to fit. So now we're just going to pull back to an ideal on P6. So what do I mean by this? So this is an old construction, well, it's a slightly generalized form of, I think, Ferrand. So let me look at the nth order infinitesimal neighborhood of this P2 and P6. So I get the ideal sheaf of this to the L plus first power, ideal sheaf of lambda to the nth power, and then I have the sim L of the conormal bundle. Okay, so this is just what it looks like if I take this is just the power, the nth power of the ideal of a linear space mod the L plus first. I get a picture like this. And now here, I have this subsheaf EK twisted by minus L. Okay? And so, this is just the isomorphism theorem in algebra. I have a subsheaf of a quotient that gives me a subsheaf of this thing here. So I can pull it back to, this gives me some ideal. This gives me some ideal. I'll call it J, so it's not a multiple ideal. This gives me an ideal, some kind of random ideal J inside the nth power of the ideal of the P2 and P6. I just pull it back. So I just form an exact sequence like this. So what does this J look like? Well, who knows? See, J is some funny ideal, and it defines the support of J. So J defines a scheme, some weird scheme supported on this P2 and P6. So it's some weird sheaf supported on this P2, but it's got some kind of funny nth order infinitesimal structure with some funny, it's hard to really visualize, funny nth order structure. So it's a completely non-reduced thing supported on P2. I'm putting some really weird scheme structure on P2 that I don't understand terribly well geometrically. But it's an ideal, and now we're good, because if you can just run the exact sequence, and, well, OK, so let's see. So let's see what this J looks like. So J is not a multiply idea, but I didn't want to. So first of all, I claim that J twisted by L plus 1 is globally generated, just because the two outer terms of that sequence are. I haven't yet really mastered this. OK, so it's some kind of weird scheme. In any event, it does its purpose. So note that J twisted by L plus 1 is globally generated, just because you can kind of see that E is E twisted by L plus 1 globally generated, and so is this power. And then you can just use what we know about E to compute its regularity. And so what's the regularity of J? Well, it turns out to be K plus L. But what's that approximately equal to? So remember, L was so K is approximately L to the 3/2. So this is approximately times L to the 3/2. So this is an example where I have an ideal sheaf. When I twist it by L plus 1, it's globally generated, but the regularity is a polynomial in L of degree bigger than 1. So this is already well beyond the complete intersection range. But this is, in some sense, it's still a very soft construction. So I think a kind of a very interesting problem that I think it's a nice construction that certainly advances the story. But I think it's still an interesting construction to sort of find, interesting problem to find geometric constructions of ideals closer to this weird, closer to this Meyer bound. So remember, what's known is that you can find ideals where the regularity is like L to the 2 to the number of variables. So, and again, the broader problem is to find some systematic way of producing ideals with large regularity, because then you'd have some sense of what's possibly true and what's possibly not true about regularity. OK, so in the last 10, 15 minutes, I want to just talk quickly about Casanova regularity bounds. Casanova type regularity bound. So, as I said, the study of Casanova-Mumford regularity, it's a big thing in algebra. But if you ask the algebra people what's the sort of interesting question, nobody would talk about these things in terms of defining equations, although it's a question that I'm fond of. But it's about the degree of the variety. So I just want to mention quickly what's known and not known here. So this starts with a classical theorem of Casanova about curves. So let me state his theorem. OK, so we consider a smooth non-degenerate, so that a smooth non-degenerate curve. So that in P3, and non-degenerate means it doesn't live in a P2 of degree D. And then what Casanova proved is that then hypersurfaces of degrees, let me move this up a little bit, hypersurfaces of degrees greater or equal to of degree greater or equal to D minus 2 trace out a complete linear series on C. So in other words, i.e., remember what that means is that H1 of the ideal sheaf of 3 twisted by d minus 2 is 0. And hence, I'll put this in quotes, hence C is d minus 1 regular. So this is the classical theorem. So why do I put this hence in quotes, and why do I say this? So remember, if you have a curve in P3, then if you want to study the ideal sheaf, the common of the ideal sheaf, this H1 measures whether something traces a complete linear series. But the H2 of a twist of an ideal sheaf is the H1 of some line bundle on C. So once you have, the H2 of this thing you can control easily. And so this, this is the important point, and then you see that you get that regularity. Okay, and so, and this is the best possible if you take a curve with a d minus, so you can write down curves on quadrics where you can't do any better than this. And so somehow in the early 80s, people looked at this, and then Joe Harris asked the question, well, if you have a curve, the obvious examples where this is optimal all are curves in P3. So Joe raised the question, if you have a curve in P4, P5, could you do better? And so this was something that Gruson and Peskin and I looked at. And you can do that. So the sort of generalization here is that if you take a curve in CR, in PR, non-degenerate, so not in the hyperplane, in degree D, then you can do a little bit better. So then C is, you get this is D plus D plus 2 minus R regular. So D plus 2 minus R regular. So as you go into bigger, each time you go to a bigger projective space, you do a little bit better. And again, it's optimal for certain curves that you can write down. Okay, so this raises, okay, fine. So this raises the question, what happens in higher dimensions? Okay, so there's a kind of a natural extrapolation of this statement. Okay, so what's the natural extrapolation of this? So that's unfortunately not a theorem, it's a conjecture. So the obvious extrapolation of this statement, so let me call it the regularity conjecture. You want to bound the regularity of a smooth non-degenerate. So if xn in PR is smooth, non-degenerate of degree D, then the regularity, so non-degenerate again means it's not in the hyperplane. Then let's see, the regularity of X, if I've got the numbers right, should be less than or equal to D plus N plus 1 minus R. So I just replace 1 by N, the dimension. So this is the obvious extrapolation. And sometimes this is known as the Eisenbud-Godot conjecture, because they were the first people to actually write it. I mean, obviously people had thought of this before, but they wrote it down. They asked whether it's enough that X be, let's say, reduced and irreducible. Anyway, so this is, I don't want to, I was going to show you a proof in small, but anyway, it's OK for n equals 2. There's a kind of a vector bundle argument, and n equals 3 almost. There's a kind of an argument with vector bundles that gives, I think the numbers degrade by 1, and for small n, it has to do, well, I don't want to say too much about it. But I have this is, there are literally dozens and dozens and dozens of papers in the commutative algebra community not proving this. But I have the feeling that somehow this is probably, if you take smooth things, I have the feeling that it could easily not be as hard as, I'm not convinced it's that hard. Of course, if I knew how to do it, I wouldn't be here telling you it's a conjecture. But what's the sort of best result along these lines? So the best result is actually by Mumford. So let me state Mumford's result, and then I'll show you how you can deduce it from this regularity theorem, and we'll do it. So again, here it doesn't matter smooth, degree d. Then he gets a bound that's, so again, the important thing is that he gets a linear bound in the degree, but there's a parasitic component. Then the regularity of x is at most something like what? N plus 1 times d minus 1 plus 1 regular. So the point I want to make here is that, see again, this is what I was saying before. You get a bound that's at least, so here the input geometric data is the degree. And you get a bound that's at least linear in D. But it's also known, there's a construction that you can take a kind of this weird Meyer deal, and you can find a sort of a really terrible, reduced, but not irreducible ideal in a big projective space that has horrible regularity. So the point is that at least it's, in this smooth case, it's linear in D, but I mean, again, you'd like to have the coefficient is wrong. But anyway, so let me end by showing you a proof. This isn't how Mumford did it. Mumford's theorem via this regularity theorem we did earlier. Again, it's not totally clear. Well, anyway, so let's do this. Okay, so the main remark, well, there are two remarks. So it's almost to deduce it from this regularity thing, but it's interesting that you get exactly the same numbers. So if you have a smooth n-dimensional variety in PR, as you know, if R is big, you can already project isomorphically into P2n plus 1. So, so by taking a general projection, we can assume that R is at most 2n plus 1, and therefore E, the codimension, is at most n plus 1. And so why can you do this? So the point is, if you take let's say you have a curve in P4 and you want to prove a regularity statement and you project to P3. Well, what's always, so remember the cohomology of the ideal sheaf, the cohomology from H2 and above is just intrinsic. It's cohomology of line bubble on the variety, so that doesn't depend. And the H1 is whether or not things cut out a complete linear series. So regularity gets inherited up. If you have a vanishing of the H1 of the ideal sheaf in a smaller projective space, that means smaller hypersurfaces in a smaller projective space trace out a complete linear series. So a fortiori, they do in the big one. So you can always project down. So we're in that situation there. And then we're basically done because there's this classical lemma. I know it from Mumford, but it may be earlier than that. So if you're given a smooth projective variety xn and PR of degree d, then X is cut out as a scheme by hypersurfaces of degree D. So anything a variety of degree D is actually cut out by hypersurfaces of degree D. And why is this? So what are the hypersurfaces? You take cones. So, I mean, this is basically the classical argument that says a variety is determined by its Chow form. So let me just. Okay. Okay, so that's Mumford's lemma, and the proof is you take cones. The proof of Mumford's lemma is you take cones. So let me draw a picture in P3. Supposing you have a curve C in P3 of degree D, and we want to say that it's cut out by hypersurface in degree D, so we take cones over C. So if we take a cone over C, that's going to be a hypersurface of degree D. And as we vary the center of the cone, we get a bunch of hypersurfaces, and those, you check those, cut out the curve. So the proof is take, if you have an X, smooth X, take cones over X, centered at linear, whatever you need to do to get centered at linear spaces of dimension, whatever it is, so R minus N minus 2. So in case of curves, you would take cones, or it's centered at points, and you'd vary the point, and you get a bunch of cones, and those cut out the variety. And now we're done, because, okay, so now we apply the regularity theorem. So the theorem we talked about. So what does the regularity theorem say? So a regularity theorem says that the regularity of X is less than or equal to the codimension times D minus 1 plus 1. But you see, we've said that we can, because it's cut out by equations of degree D, but we've said that we can assume that the codimension is less than n plus 1. So this is n plus 1 times D minus 1 plus 1. So you get the right thing. So it's kind of strange that you get exactly the same answer, because nobody's imagining that this is. But let me just end by spending, let me have 3 or 4 more minutes showing you, giving you roughly the idea of Mumford's proof, because it's very interesting and it raises an interesting question. So what was Mumford's idea for this? And I think he was inspired by this. So the classical theorem of Casanova, what Casanova did is he projected the curve to P2, and he looked at a singular curve in P2 with nodes. So then Mumford's idea was to look at projections to n of an n-fold to Pn plus 1. So what Mumford's going to do, he's going to take a general projection, pi, from xn to Pn plus 1. So we're going to kind of realize our variety as birationally as a singular hypersurface in Pn plus 1. So if we had a curve, we project to P2, and we get some kind of we get a curve with nodes. Okay, and now inside, if you have a general projection like this, inside X you have a double point divisor. So let's say d pi is the double point divisor, the divisor of double points. So it's where this map, it's the set of points on X over which this map isn't, right? There's going to be a divisor on X over which it fails, along which the map fails to be an isomorphism. And it's classical, the classical, this is D minus n minus 2 times the hyperplane minus the canonical bundle. Right, this is saying that, this is the famous fact, if you have a singular hypersurface, the canonical, it's like if you have a curve in the plane with nodes, the canonical bundle on the smooth things is curves of degree, n, we're in Pn plus 1. So, curves of degree d minus 3 through the nodes. So this is just the classical adjunction thing. And now the point is that this is what's called the conductor ideal. So let's consider H naught. I'm going to use H for the hyper. I'm going to use mixed metaphor. So I have OX of KH, so hypersurface degree K on X. And inside here, I can look at those that vanish on the double point divisor. So H naught of X, O, KH minus the double point divisor, d of pi. So let me call this V of K comma, V, K comma pi. So these are all I'm trying to say that if I choose K large enough that all the sections of this line bundle come from the ambient projective space. And these are all the sections of this line bundle that happen to vanish on this double point divisor. And what's classical is that the sections in here actually come not only from the ambient projective space, but they come from this Pn plus 1. So the point is that the sections in Vk pi, I'm going to come from actually Pn plus 1. And so I mean, anything that vanishes on the double point divisor really is coming from a section in Pn plus 1. And so now Mumford's idea is to, so what he does is that Mumford, you vary pi. You vary the center of projection. So as you vary the center of projection, you get, for each center of projection pi, you get a subspace in here, and then you have to ask yourself, as you vary pi, when is the union of all these subspaces equal to the whole thing? And there's some Cazul complex you write down, and you chase your way through it, and you get the right answer. And you see this parasitic factor of n plus 1 is coming because you're kind of working your way through a Cazul complex. So that's somehow there. But you see, if you go back to this sort of regularity conjecture, I said that this statement was true for n equals 2, for example. And the argument for n equals 2 is you project to P3 and you do some vector bundle construction on P3. And the vector bundle, the numbers are good, but the vector bundle construction won't work in higher dimensions because you get weird singularities of the projection. But somehow, the temptation is to somehow go back to these low-dimensional arguments and try to vary the center of projection. And I don't see how to do that. And then let me just end by a nice question of a quark, Sijun quark. If you go through Mumford's argument, it turns out that if you could answer the following question, you could get perhaps a much better statement. You might be able to get a kind of a degree 1 linear bound. So you have a variety in Pn, and you look at various a variety in PR, and you look at various projections pi like this. So for each pi, you're going to get a double point divisor, d sub pi. And now all the d sub pi's are in this linear series. And so the question is, as you vary pi, what's the codimension in the complete linear series here of all of the linear series spanned by double point divisors? If you could answer, if you've got a good answer to that, so already for curves, it's not obvious. I mean, take a curve in PR and project it to P2. So each time you get a projection to P2, you get a double point divisor where your curve in P2 has nodes. And that, you know, you can write down the linear series where that divisor is. So as you vary the projection to P2, what's the dimension of the linear? I mean, how big a linear series do you get spanned by these nodes? And I don't see how to do that. But if you could do that, you might be able to get his quark points out you might be able to get a good answer. Okay, so I think that's it for today. And then starting on Tuesday, I'll start talking about syzygies. Okay, so that's...